Well, today I've been asked to talk about what it takes to take AI to the next level. Well, it really is remarkable just how recently everything came forth. All we hear about is AI now. It's changing the world. It's disruptive. But it's not really that recent. If you go back to July 1986, this was a cover of High Technology magazine. You can see it says heavyweights, or artificial intelligence, heavyweights get into the act. Yeah, it's not the people. That meant Texas Instruments jumping on it. And if you look very carefully at that picture, you might recognize that I don't think I look that different. After all, I was just preparing to join the EDA industry, getting a little AI behind me, and I wasn't the only one. 1986, I'm sure you'll all recognize my friend Art DeGius. That's 1 year after he received his PhD, and not only that, he had published a rule-based expert system on IC design called Socrates, so he was already into the AI game. Now, 1986, where was Lip-Bu? Lip-Bu was founding his first major investment in what turned out to be a blockbuster, Creative Labs, the Sound Blaster cards, tremendous success, launching him on his way, and then eventually into the EDA industry. And then there was Alberto. Alberto got in long before the rest of us. In fact, by 1986, he had already been teaching at UC Berkeley for 10 years. You can tell those students cause a lot of gray hair. It wears on you, but I gotta hand it to him. He looks the same today as he did back then. Actually, I'm just kidding. There's Alberto, if we go back, a young-looking guy getting started in the industry. Well, it wasn't just future EDA people that were talking about AI, and it wasn't just 1986. Go back to 1956, the AI conference at Dartmouth that had lots of visionaries there to talk about the future. And they made incredible projections. For example, within 10 years, a digital computer will be the world's chess champion. Pretty close, not 10. It turned out to be 40 years, but close. We had Marvin Minsky, who started the AI lab at MIT. And from 3 to 8 years, we'll have a machine with the general intelligence of an average human being. Now, I think that says more about the decline in the average intelligence of a human being than it does the growth of AI. And there were others, but the one that I think impressed me at the time, the movie 2001, A Space Odyssey, 1968, and here they had developed a computer that had human-like characteristics. It actually killed some of the crew, so they couldn't identify it as IBM, so they did a shift left one letter and called it HAL instead of IBM, HAL 9000. But we go to 2001, where were all those human equivalent computers? Even if you go 15 years later, what did we have? We had neural networks that could distinguish cats from dogs. A bit of a shortfall relative to the projection. But you have to ask, if all of this existed for all that time, more than 50 years, what's the reason? And so one of the reasons is they didn't have big data to analyze. They didn't have the Internet of Things. They had limited computing power at the time and traditional computer architectures. They had a need for more advanced algorithms, but the biggest thing was they needed killer applications for which you could make money, which is why TI gave up on it. Well, one by one since then, these limitations have been going away. The thing that I think has to drive any new technology is the killer apps. And that's something that now we're seeing emerging. The killer apps that can make money. But then, making money is a little bit of a mixed bag here. We have OpenAI. Last year, they invested $540 million on ChatGPT. And that investment has yielded a return of a loss of $700,000 a day every day that ChatGPT runs. Not a great investment. $75 billion spent by the automotive industry for autonomous vehicles with no really meaningful return yet. And then we have the EDA industry, tremendous progress, great products, but does anyone actually pay additional money, or do they just choose the AI product instead of the existing ones? Well, there is one person who has made a whole lot of money, and that's Jensen Huang. So we have NVIDIA, $7 billion in sales last quarter, $1 trillion club now. And if you think about selling AI hardware and software in their case, which has generated a lot of money, what's really generated the most money for them and others is talking about AI. So if you look at the number of mentions of AI in the shareholder quarterly conference calls and just count them up and plot that versus the 12-month increase in stock price, you can see that NVIDIA is the clear winner. 107 mentions in a 40-minute call, and far outpacing the competition, almost double what Alphabet did. So it's created a growth in enterprise value, not just for NVIDIA, but for lots of companies. Well, how about EDA? What has AI done? It's actually been remarkable, but I go back 15 years when I was first exposed to something that I didn't realize was sort of the same thing that is happening today. And that's we were doing high-level synthesis, and our customers discovered that rather than starting a new design by writing some RTL, if they did C simulation, then they could do 1,000 times as many alternatives as they could writing RTL. And therefore, they could explore the design space of possibilities, and just statistically, even if they had no reinforcement learning, no guidance of what to guess, just randomly, they could come up with a better solution, a global minimum for area or power or something like that. And in fact, NVIDIA and Google both latched onto that, they designed their data paths with it, and it became a way that you could use the statistics to create a better design. Well, as we move forward, we've seen AI applied to essentially everything in the design flow. At least for two of the major companies, pretty much a complete portfolio of AI capabilities. And what we've seen thus far is what I would call self-optimizing tools and flows. So basically, tools that we were already used to using have now suddenly gained in efficiency and become much better because of applications of AI principles in general. So what's it take to go to the next level? And the answer is data. The same thing that ChatGPT did to shock us all is capable of happening in EDA, but it means moving from supervised learning and reinforcement learning to unsupervised learning to have unlabeled data and be able to have the machine learning model learn and reinforce itself and gain greater capability. And then ultimately, what I'll call generative design, although some would say we're already some types of generative design, but getting to deep learning on megadata and generating new data takes us to the next step. So let's talk about the tools that have been introduced over the last 5 to 10 years. The architectural exploration tools have been remarkable because they've done just what I described with high-level synthesis, but they've taken it far further and provided intelligent reinforcement learning to explore the solution space. Functional verification has really undergone a step function improvement. So with 5% of the simulations, you get 90% of the useful information. Or with Cadence has talked about with Excellium that with less than 10% of the tests in a regression suite, you find 90% of the bugs. So it's reduced time to closure, and even in PCB, system design optimization, AI has been applied. In design implementation, optimizing power, performance area, automated porting, not totally automated, but certainly a great reduction in the effort, and it's impacted the analog space as well, and test. Fewer test vectors to achieve a similar or better coverage. Well, an example that I thought illustrates this really well was given by Art DeGius at the Hot Chips conference, and I've just taken one of his demonstrations from DSO AI, and here he was demonstrating what the tool could do for die size and area versus maximum frequency. And he started, this is untrained behavior for the model. There's the best the humans could do. It was satisfactory. But if you allow the software to go explore the space in an untrained manner, you generate superior solutions all over the possible space. So the net result, a lot of improvement. In fact, quantitatively, smallest die size was 18% smaller. The performance, if you took the extreme case, would be 15% faster, or you could trade off the two and end up with 8% faster and 11% smaller. Impressive results. Well, what about, as we get to this next frontier, the next level of AI, the design assistant that now becomes your advisor in doing a design, where it takes advantage of a foundational model to improve the learning, the insight, the ability to now understand the intent in a design and to recommend design strategies and adjust to design styles. This goes back to what the Stanford Institute for Human Centered AI postulated and demonstrated quite some time ago, and in fact was followed by ChatGPT, and that is you take a whole lot of data, much of it unlabeled, and so instead of in a traditional supervised learning where you have input features and then you have labeled outputs that are desired, this is a cat, this is a dog, you have unsupervised, and you're able to build a foundational model based upon large amounts of data and create reusable components, and then you can learn on top of the foundational model. So with the design assistant, that makes possible design recommendations, all sorts of analysis, optimization, finding similar solutions as you explore the design space. And then, as we get more and more data, as we do more deep learning, we get to the point where we can generate new data, we can have self-supervised learning, and then the ultimate, as Alberto talked about on Monday, do you get to the point where you verbally describe the requirements for an integrated circuit and it pops out the integrated circuit design? Probably not. But it could pop out a lot of alternatives you could choose from and form the basis to optimize and greatly reduce the effort for development. Well, with that, we would then be able to take all of this data and then enhance it, generate more data, and do actual debugging, not just identifying bugs, but actually getting recommendations for alternatives to fix it. Still need a designer, still need to take the advice, but in general, you move to an environment where you really can think about from requirements to actually design blocks. Well, so all we need is data. So I'm sure all of you semiconductor people will be happy to turn over all your design data for the greater good, and we can build a database. But the fact is, people are somewhat unwilling to do that. So you look, there are public databases. ImageNet, for example, 15 million pages, sounds like a lot. It's not a lot. It's far too limited for the kind of training we're talking about. What about if you had a database of all designs ever done by your company? Well, maybe. But that has very limited utility. A designer doesn't want to know what existing design he can copy. They want to know how you got to that design. You really need the design journey. You need a database in your company that covers all of the design journeys, and most companies don't archive all of the various revisions once a design is done and in production. So that's data that's not easily available. And it's not only that. You need more than the design journey that was successful. You need the unsuccessful journeys as well, which nobody archives, but which gives you a great deal of information when you're trying to decide where to go from a place you've gotten to. So we just need a way to create, store, and share that data. Well, secure data sharing, I believe, is one of the biggest barriers to going to the next level of AI as applied to not only EDA, but the whole space of opportunity. So, with secure data sharing, we have all this data coming in, and 2.5 quintillion bytes a day by some metrics, and we only use a very, very small percentage of it, at least so far, and yet it contains all of the wealth of everything that humanity has created in history, all of the trends, other information, and it's increasing, and it's stored around all sorts of places around the internet and in various databases, an enormous data sharing opportunity if you could tap into it. But you see with ChatGPT, where they took an enormous base of data and built one of these foundation models, it's remarkable when you use it, but it's also unreliable. You get wrong answers sometimes. They sound good, but they can be misguided based upon what's in the foundation model. There's copyrighted data used. There are security threats. A lot of companies aren't allowing their employees to interact because they know that that information will then be passed on and built into further learning. So a lot of limitations. But if people are going to actually take data and clean it up, make it reliable, get rid of the copyrighted information and all that, that's a lot of work. And the problem is you build a machine learning model, and guess what? Somebody steals it. In fact, theft of machine learning models has become rampant. Headlines everywhere for how to steal a machine learning model, how to steal the data that has built the model, all these kinds of things. In fact, Tesla learned that lesson the hard way. Their neural network model for the autopilot feature was copied by one of their competitors within a month of introduction. And at the hackathon in Vancouver, they were able to hack into the Tesla machine learning model in less than 2 minutes. So it's very difficult to protect that kind of data. So why would you invest a whole lot of money cleaning it up if it's going to be stolen? Well, the answer is you can. You can share data without disclosing any sensitive information. Now, with that, there's a strong economic motivation of the owners of data to take advantage of it, to market it. You can build proprietary machine learning models without anyone copying them. You can share sensitive data without revealing the actual data. And once that becomes commonplace, then database owners will, in fact, invest in data collection, in quality, reliability, copyright-free data. They can then monetize it. They can charge per query, and they can promote their own quality differentiation. Well, so how will secure data sharing become possible? The answer is something invented right near here, Stanford University, 2009. Craig Gentry invented fully homomorphic encryption. That is the ability to keep data encrypted at all times, but to perform computation on the data while it remains encrypted. And you can even build machine learning models from encrypted data. So how does this work? Well, we have you, the client, has some data. You encrypt it with a very secure form of encryption that is believed to be quantum proof because it's lattice-based and no one knows how they can make quantum computers break it. And then you send it off to the cloud or wherever, and you perform a lot of computation on it. It's never decrypted. No one else has a key. No one ever sees the plain text data. and the answers from your computation are sent back to you, still in encrypted form, only you have the key, the data is always protected. Well, with that, once that's in place, then all sorts of people in all sorts of specialties can take their data and market it, sell it, gain benefit from it, invest, improve the data, not just EDA, but medical analysis, financial data, all sorts of specialties where you can build databases, and then we can take advantage by doing queries to your encrypted model. And the billing only occurs when you give us the key to decrypt the results, but you never see the actual data or even the data model. Well, hey, this sounds really great. Why doesn't everybody do this? Well, there is a minor problem. FHE is a very hard computational problem. That's why it's so secure. That's why it's quantum proof. Take a simple logical operation like a two-input and you have a bit there at A, another bit at B, and that bit has to be converted into a 500-order polynomial with double precision floating point coefficients. And then the AND operation just requires 3,000 1,000-point complex 64-bit floating point fast Fourier transforms, and that's not even the whole algorithm. That's just a portion of it. So when you try to do that, you find the data expansion goes from about 4 bytes in a case would go to 1.7 megabytes, and one CPU operation would go to more than 12 million CPU operations. And then there's the problem that all this computation generates noise, so you have to do what's called bootstrapping. That's more overhead, so it's really, really slow. Plain text computing, some computation you did on plain text data in 1 second, if you encrypt it and do the computation while it remains encrypted, that will require 11 days. Well, it doesn't sound very practical, although there are applications out there, Election Guard from Microsoft, for example, where they didn't have a time limit on adding up votes. They just wanted to be sure it was secure. But not many applications can tolerate that. But all sorts of innovative people have been working on this for almost 15 years, and they keep coming up with new innovations. And so what you see here is a chart of the normalized performance, which has improved 7 or 8 orders of magnitude since the invention in 2009. So we're on track to get there, but things have flattened out a little. And so software alone is not going to take us there. You're going to have hardware acceleration, enter the EDA industry, design some hardware. Well, there are other things that are making this easier, and one is standards, so that we all work with the same FHE standard. The Rosario Camarota from Intel is heading up the ISO Standards Committee. They have a draft standard. They'll have the final standard next year. So that helps things some. And then we have the DARPA DPRIVE program, which is close to $50 million, and they had 3 phases. The first phase, companies develop better software algorithms. The second phase, they show how that can be reduced to a silicon design. And in the third phase, which by the end of this year, they will choose one company at least to actually do a chip design to do the improved performance. So lots of advances coming. There are co-processors to accelerate particularly the fast Fourier transforms, and then the software is still advancing. New advances show up every month. So what's it going to require? Well, one of the problems with fully homomorphic encryption is it's a data movement problem. Traditional von Neumann architectures just don't work. You can't read and write to memory. You can't follow the normal approach that we've become used to with Intel, NVIDIA, other processors. So as you increase the number of processor cores, shown there on the horizontal axis, the performance improves for 4 or 5 cores, and then Amdahl's law sets in. Then the need to synchronize and to coordinate the computation, shared memory, other functions, drag it down. So addition of more cores actually slows it down rather than speeding it up. What we're going to need is some really unconventional computing. DARPA talked about laws, the large arithmetic word. When we say large word width, we're talking 10,000 bits or more in word width. We're talking massive parallelism, distributed memory, deep pipelines, as much as 100,000 stages deep, a massive number of cores in a very small footprint, and programmable hopefully via one of the 6 major FHE frameworks. Well, that's a pretty tall order, but that's going to be impacted very quickly. The approaches that have been announced are mostly take the algorithm and just reduce it to silicon, implement a single algorithm that has the disadvantage that it won't evolve as the software evolves, but it would get us very close to the performance, or at least within a few orders of magnitude. There are lots of coprocessor attempts. There's one company doing optical computing, optalysis, to accelerate the fast Fourier transforms, and one doing reconfigurable computing, programmable parallel processors. I think for the future, the problem is it's early in evolution, so you need as much flexibility as possible. You need to be able to adapt to new algorithms. You need to be compatible with the different frameworks. So a lot of challenges ahead, but we're getting close. So over the next 2 years, we will, in fact, have the capability in place. So then the issue is who will use it, how will they take advantage of it, and the impact across industries is very, very promising. There are data sharing opportunities in almost every industry. Financial services is a good one because the financial impact is great, so they're early adopters. If you talk to any investment bank, you'll find they have a fully homomorphic encryption group already developing applications for things like analysis of data for insurance companies or investments, proprietary models, data sharing for financial institutions across borders to look at fraud prevention, money laundering, things like that. In fact, the major banks are deeply into this already, and what they're planning to do is they have all sorts of highly proprietary data that they cannot reveal, and yet, if they use fully homomorphic encryption, they wouldn't reveal any data. That data could be shared with other banks. You can build a database, and then you can do queries and see where money transfers occurred and get information back. Everything remains encrypted, even the queries, so privacy is maintained, and yet you get enormous insight into what's going on in the flow of money. Healthcare. One of the great ones, one of the big impacts, predictive diagnostics in particular. And you're already experiencing it today. If you have an X-ray or an MRI, it's assisted by the database of information. But the larger the collections of data we can get, the more powerful the predictive diagnostics will be. Unfortunately, patients are largely unwilling to share their personal medical data. If you have an exam and the doctor asks you, do you mind if I turn your data over for the good of mankind? You probably say, well, is this going to affect my medical insurance rates if they find out about it? Or people just don't want to do this. But if it was truly protected from being found, it could change the way we collect data and the ability to convince people to give their data. And not only that, but China is way, way ahead of the US. They've got 1.4 billion people who are much more likely to provide their medical data through their national healthcare system. They're not going to share that with us, but if everything's encrypted, you can build an even better and a bigger machine learning model. So the big advantage here is you can encrypt the data at its source and then build the machine learning model from encrypted data, and then you can make encrypted queries to an encrypted model, get encrypted results, and ring the cash register when you get your diagnosis. Really powerful. It's called privacy-preserving machine learning. Well, What about industrial equipment? This is a great one because my history in the semiconductor industry, we were very reluctant to let the equipment providers know what we were using their equipment for. We just felt that our proprietary processes would leak to our competitors, so we didn't want them analyzing our sensor data or anything else, and yet they have enormous power to improve the performance of those machines. So what if you could encrypt the data at the sensor and then give access to the encrypted data? They could then take thousands of other machines that were essentially identical and build machine learning models that could give insight into predictive maintenance and yield, throughput improvements, energy efficiency, enormous benefit for everyone, but you've got to get access to that data. Now, I can show you an example where data security is not important, where exactly that has happened in the aircraft industry. The makers of jet engines, Pratt & Whitney, GE, Rolls-Royce, those people, when they sell the engine, they also sell you a maintenance contract to monitor the engine. So I was in 2014, I was really surprised when Malaysia Airlines 370 going from Kuala Lumpur to Beijing disappeared off the radar, stopped transmitting, and yet they were able to track it for 2 hours after it disappeared because the engines were transmitting data to satellites. That data is collected, and so a manufacturer of the engine can tell you through machine learning models all sorts of things about predictive maintenance or any other sort of problem. And if you're an airline, you'd be crazy not to pay for that. So the net result is they can charge more and more for the maintenance contract because you're going to have to buy it, and less for the equipment. So that takes a bumpy or lumpy business into a much smoother business and has a lot of benefit. Well, there are some limitations to passing all this data around, and one is all the data regulations that are appearing. So regulatory protections are becoming significant and costly, and trying to collect data and transmit it internationally is becoming more and more of a challenge. There's greater willingness to share the data if it's encrypted, but it isn't currently, and there's also the issue of passing data around that's copyrighted and other things, so people want to protect that data. Well, if you just look at the fines, most recent one in May, Meta was fined 1.2 billion euros for the GDPR regulations of protection of personal data, and other fines. If you just look at up through last year, $2.4 billion in fines just for GDPR. So people are getting very sensitive about protection of their data. Now, fortunately, latest IEEE standard for biometrics has in it, if encrypted with fully homomorphic encryption, then you are GDPR exempt. Same thing has been true in legal reviews and audits. So basically, if your data is sitting in a computer center and it is encrypted with fully homomorphic encryption, then you have none of those regulatory worries, not to mention the cost of lawsuits for disclosure of data. All that goes away. Well, this is very timely in a way because both AI and cybersecurity moving to the next level now are being pushed by another thing, and that is what you heard yesterday. Quantum computers, once they get to about 10,000 qubits, are going to break most of the security in the internet. They will not break lattice-based encryption, but they will break most others. And the number's a little different from what you heard yesterday. Google's a little ambitious at 1 billion by 2030. I believe the number was more like 100,000 or so. But anyway, whatever it is, they're going to pass that limit. It's going to be broken, and this is the sword of Damocles, impending doom that is occurring. So it's inevitable that we will have to upgrade our encryption. So What's it all say? Well, first thing, your design data is valuable. You need to start archiving it, both successes and non-successes. You need to put it together, form alliances with other companies to share data if you believe you can both benefit, and you can. Build foundation models that will power your design assistant and store your design experience. Entrepreneurs have a great opportunity to put together databases that they can rent out and sell and generate money, and the design data always remains protected. And when FHE becomes commercially viable, and it's within the next year or two, then the world changes. Then data sharing becomes a profitable repeat business without fear of exposure of sensitive data or loss of a valuable machine learning model. The privacy-preserving machine learning means that we'll be building models based on encrypted data, and so the value of data will increase through sharing and through building larger databases. And regulations and liabilities and business opportunities will drive all sorts of things because people really want to comply with the regulations. And so what we have to do, of course, is advance the hardware along with the software and close the last 5 or 6 zeros of performance. A tough job, but I'm quite confident it will be done, and much sooner than you think. And next generation scalable computing will solve that problem. And the regulations that appeared so onerous will not be so onerous in the future. So intelligent design assistants will become possible with EDA foundational models, and we'll be able to share data, experience, and expertise, and that will take us to the next level of AI. Thank you.